All right, today I'm going to talk to you a bit about stoichiometry. So, stoichiometry is the use of molar ratios, right, to predict the quantity and mass of products. I'll put both those together. Right. So, in industry, they're always worried about what our yield is going to be, or how efficient our yield is going to be. So, they use stoichiometry to predict how much we should get, or what's called the theoretical yield. So stoichiometry calculates what's called a theoretical yield. And then I can look at what my actual yield is. So my actual yield would be what I would get in an experiment. And then I could try to tweak things to make it more efficient. All right, since stoichiometry is going to be based on moles, which we learned about, and chemical equations we learned about, it will follow the laws of conservation of mass, matter, and energy. So just like a regular chemical equation, it'll follow those same laws. So if we take a simple example, right? So cooking uses stoichiometry. So a lot of you have done stoichiometry, but you didn't know what it was called. Right, so if I take 4 pieces of bread, 2 eggs, a quarter cup of milk, I'll get 4 pieces of French toast. Right. So well, that does sound good, doesn't it? So if you have a loaf of bread at home, you have a dozen eggs, right? And you have a gallon of milk, how many pieces of French toast could you make for you and your friends? Right, so there's a chemical way to do this. So we look at molar ratios, right? So molar ratios are based on coefficients. Right? So we could go through the molar ratios here. So remember, I'll put it over here. I have 4 bread plus 2 eggs plus just to remind us, right? So that's my equation, or my recipe. So if I'm going to look at the above example here, right? So if I have a loaf of bread and that loaf has 20 slices, right? My ratio in my equation here of bread to French toast is 4:4, or it's a 1:1 ratio. So for every 1 piece of bread I have, I can make 1 piece of French toast. If we look at eggs, right? So eggs is here. So my French toast to egg ratio is 4:2 or 2:1, right? So I can make 2 pieces of French toast for every 1 egg that I have. French toast to milk is 4 over 0.25 or 16:1. So for every cup of milk I have, I can make 16 pieces of French toast, right? So now we can start to use these molar ratios to figure it out. So if I want to know about bread, I could just simply do it like this. If I have bread, and I want French toast, stoichiometry lets me convert between 2 different things. All I have to do is use the molar ratios, right? So this is 4:4. If I have 20 pieces of 20 pieces of bread to start out with, I can make 20 French toast. If I want to know about the eggs, I have 12 eggs. I want to make French toast. I want to get rid of my eggs. I want to use them up in the process. My ratio, remember, French toast to eggs is 2:1. So I can put my 2:1 here. So with 12 eggs, I can make 24 French toast. If I look at my milk, right, I have 16 cups of milk. I want French toast. I want to use my milk in the process. Remember, now my ratio is 16 to 1. I need a calculator for that one. With a gallon of milk, you can make 256 French toast. So if I look at all of this, the maximum amount of French toast I can make, holy moly, the maximum amount of French toast I can make is that. So this is what's going to call, and we're going to talk about this tomorrow. That's going to be called your limiting reactant because it limits the amount of product you can make. So after you make your 20 pieces of French toast, you can still have 4 eggs for breakfast, right? And you could still have a bunch of milk to drink with it. So that's stoichiometry. And I'll show you how to do it in real life. This picture right here is probably going to be one of the most useful things that you have. And you probably need to take a picture of this and use it for your quiz and your homework. Because this is your roadmap. Remember we had a triangle roadmap for moles, right? So we have a modified triangle for stoichiometry. The important thing here is right here, we find this equation, which uses our molar ratios, right? And the molar ratios go in that parentheses. So this mole to mole using coefficient, this must be used in every stoichiometry problem. So you must have this step. If you don't have that step, you probably didn't do it right. So I'll show you how to do it. So solving problems, right? So that's the mole to mole. We just talked about that. I'll give you some examples, right, for your homework. All right. So I give an equation here. So I have the equation here. We have molar ratios of coefficient. Remember, if you see something without something listed in front, it's the assumed one. Okay. So if you start with 5 moles of Cl2, so we'll put that here. Substance you start with. Right. How many moles of sodium chloride could I make? So over on this side, substance you want. Starting substance to cancel. I started with Cl2, so I want to put that down here so I can cancel. And the molar ratio coefficients. So the coefficients by NaCl was 2. So I'll go ahead and put that there. And the assumed 1 for Cl2. Right? So, pretty easy math here. I'll cancel out my Cl2. I'll end up with 5. I'll end up with 10 moles of NaCl. So that's simple stoichiometry. That's a mole to mole conversion. So if you look at this, the way you do this with your roadmap, I'll show you. Here's my start. And this is my end. Right, so if I went over here to my roadmap, I said that you need to take a look at. This is my start. This is my finish. Right, so I'm only doing the mole to mole because I had moles and I have moles. Okay? Let me give you another example. I have 100 grams of sulfur. So this is my start. How many moles of SO3? So this is my finish. If I come back to my problem here, clean this up a little for you. All right, I start with grams. So this is going to be my start, right, because it's mass. And I want moles. So that's going to be my finish. So in order to do this problem, I need two equations. I need to go from mass to mole, and then mole to mole. So the number of arrows is number of equations. If I was going to go from mass to mass, be 1 arrow, 2 arrows, 3 arrows, I need 3 equations. So let's do that really quickly. All right. So we have 100 grams of sulfur. So 100 grams of sulfur, this is my start. So I will put that up here. My sulfur comes in the version of S8. Right? So first thing I had to do was go mass to mole. That was on my list there. So I'm going to put mole here. I've already done this ahead of time, so I know the mass, right, of S8 is 256.56 because it's 8 times the mass of sulfur. And if I do that, I get 0.3898 mole of S8. All right, so I'm trying to find SO3. How many moles can I finish? So SO3 is what I want. S8 is what I need to get rid of. And I go over here and I look at my ratios of coefficients. My coefficient before S8 is 1. Oops. That goes down here. And SO3 was 8. Right? So I simply just multiply that by 8 now. And I get 3.11 moles. Right, so that's my answer. I'll give you one more. All right, I have a kilogram of octane, right? It's combusted with excess oxygen. How many liters of CO2 can be released? All right, so my start is here. How many, my question? So my end, my finish, is at liters of CO2. Let's come all the way back up here again. All right. So my start was in mass, and my finish now is in volume because I have liters. I need 1 equation, 2 equations, 3 equations. Okay? All right, so that's how you use a roadmap. So you need to have a picture of that to use on your test and with your homework. It'll make it a whole lot easier. All right. So remember, when we do a mass to mole conversion, we need grams. So 1 kilogram, so it's 1,000 grams. And I have to get a mole first, because mole to mole is going to be my middle equation. And my mass of octane, if I look it up here, is 114.26. And I do that, and I get 8.8 mole. I'm trying to find how many liters of CO2, so CO2 would be here. I need to get rid of my octane. And I go look at my coefficients. My coefficient for CO2 is 16, and for octane was 2, so it's a factor of 8. So if I multiply this by 8, I get 70 liters. See, oh, sorry, that is wrong. It's not liters. It's 70 moles. And then I need to go to liters, right? Okay, so now I've got 70 times 22.4. and I get essentially 1,600 liters of CO2. Okay, so that's how you do stoichiometry. And these would be theoretical yields. Okay, I'll give you one last problem here. If you want to pause it and try it on your own, that's probably good. If not, well, let's work through this. So again, here's my start. All right, here's my finish. The how many. Right, so if I come back all the way up to my roadmap here. All right, so now I start with moles and I finish with mass. I have one arrow and two arrows, so I need two equations. Okay, so my start is 5 moles NaCl. Right. And I want to go to grams of Cl2. So Cl2 is what I want. NaCl, that's what I want to get rid of. If I look at my coefficients here, I have a 1 here, I have a 2 there. So I get 2.5 moles of Cl2 because my sodium chloride cancels out. And now I want to go to mass. And my molar mass for Cl2 is 70.90 grams. When I multiply that, I get 180 grams of Cl2. All right, so that's it. All right, well, good luck with today's work. Remember, there's a optional help Zoom later, and I'll talk to you soon. Bye.